So, pumping lemma now. So we're going to go over first when to use it and when to not use it. To pump or not to pump. So, we're going to have two main cases. If something is regular, if something is not regular, and if something is not context-free. We need to backtrack a little bit, back to regular expressions and context-free grammars. And what this comes down to is our good friend, the links. And this is something that you might remember from telescoping grammars. If we have something like this, let's say A, B, C, G. And let's say I have to the J, to the K, to the L, that's an L, and M. There's no links between this, right? No links, that's regular. Now, if I were to switch this around a little bit, let's say that. Now, there's a link. This is your ordinary context-free grammar, telescoping grammar, right? For every one A, we have two B's. If you were to draw something like that, right, a string would look like this, right? A, B, B, and then whatever many C's and G's there are. But we don't really care about that part. This doesn't break the regular expression property. This does. See, if you were to make a regular expression, you can't really do this because you are essentially saying that the number of A's depends on the number of B's. I can't just say, oh, I'll just do this. Like, no. This is not something that you can do. Because this is literally saying A, B, B, A, B, B as many times. That's literally not what you're doing. You are literally saying you are going to have one A to the left for every two B's to the right. And you're telescoping. Because we know that if we were to make an actual grammar for this, we would have a function, let's say A, and this function A, let me get rid of this. This function A is going to literally say an A on the left, call your recursive function, two B's on the right. And you have your lambda for when you want to stop. Actually, probably two. Actually, wait, would I have two A's there? Yeah, no, this would be it. So then I call my A again, and I can put another A, capital A, B, B, etc., etc. So you see how we have telescoping in the sense that it's going to the left and to the right. It's not like that example that we had before where it was ABB, ABB, ABB. That is the difference between having something that's regular and something that's context-free. So that's the example of not regular, but is context-free. You could think of making this grammar for this example there. Now we get into the case of, I'm very proud of this, honestly. I'm a big pun person, and I like making fun ways to remember things. Links of 3, not context-free. And you're going to see why. Let's say A to the J, B to the 2J, C to the 3J. Oh no, there's a link of 3. This is saying 1A to the left, 2 B's in the middle, 3 C's to the right. If I made a grammar like this, right, how would I even do that? Something like that? No, that wouldn't work, because then I get all of these guys to the left. I can't put it in here either. I can't even put it in the middle. I'm going to wind up with things in the wrong place. It doesn't fit nicely. Because of that, links of 3 are not context-free. So, just anytime, just remember that. There's also a second case, overlapping or intersecting links. What do I mean by that? Well, in this case, shoot. I do not know where my phone went. Oh, okay. Anyway, the next case of not context-free is intersecting links. This is if you have something like this. A, B, C, and this is A to the J, C to the 2J. Bring in a G here, and this is 2K, 4K, whatever it is. I got 2 links here. Now, 2 links would be fine if they didn't intersect. Very similar to the last time. How do I make something like this with something telescoping in between when the other half of that telescope has to be on this side? It's like you're splitting telescoping. There's no way for that to work. So because of that, intersecting links are also not context-free. So I've not thought of a fun way to remember that one yet, but I'll get back to you on that. For now, keep in mind of these 2 cases that are not context-free. So this case up here requires pumping lemma to prove if not regular. This is pumping lemma for not context-free. And if it's regular, great news, it's regular and context-free. If it's regular, it could be made context-free. If it's context-free, it can't always be made regular. Not context-free if there's telescoping in between. I love it. So look at that. We got 2 things to remember. Not context-free if telescoping in between. Not links of 3, not context-free. Yeah, I think I need to get a life outside of computer science. No, honestly, I really didn't like doing this when I was taking the class, but it honestly gets better. It's actually not as bad. No, you don't. Yeah, honestly, I find that, like, tutoring it, like, it kind of makes it a little bit more interesting, because I kind of teach it the way that would be more interesting and makes more sense to me. Like, sometimes Obernick goes into it, like, very theory heavy, and that's good and all. It's important to know the theory. I'm not going to knock that off. But sometimes that doesn't help with the actual applications of it. So I kind of feel like having like the balance between that, the theory and the applications, helps the most when it comes to these exams. So before we move on, does anybody have questions on when to use pumping lemma and when not to use pumping lemma? We use it if it's not regular or not context-free, based on what the question is asking us. So if the question says, If this language is regular, write out the regular expression or the grammar or the automaton. If it's actually regular, you do whatever it tells you. If it's not regular, even if it's context-free, then you do the proof. If the question is asking if this is context-free, do whatever. If it is context-free, do whatever it is, the grammar or the automaton. If it's not context-free, then you do the proof. Everyone good? Okay, I'm gonna count the silence as either we're good or everyone's lost and doesn't want to say anything. Or you just want to watch the recording back, because totally get that. If you're just kind of vibing here and I'm gonna relearn it later or something, that's fine too. Yeah, you need to see the application, totally. But if you guys are just good with just this for the time being, then that's half the battle. I'm gonna show how it's gonna work out in just a moment. All right, cool. So if it's not regular and not context-free, you use pumping lemma. Yeah, so anytime that it's literally not regular and not context-free, then you know immediately, use pumping lemma, because it's literally neither. But if the question is asking if it's regular and it ends up being context-free, you still use pumping lemma. Let me show you the questions first, and then it's going to make a lot more sense. Can you see the exam on my screen?
No.
No? Okay. If that's the case, then I'll just post the questions themselves. Okay. This is what a question is going to look like. There's going to be two parts to it. And it's going to look like this. All right, yeah, I thought I shared my screen, but I guess it was just a tab. That's fine. Okay. So, it's going to give you a language. This one is saying if L is context-free, then use part A of the answer space to write a formal definition of a context-free grammar, and do not write anything in B. If L is not context-free, do not write anything in A, but complete the missing part of the text given in part B as to obtain a proof that L is not context-free. In English, if it's context-free, do grammar. If not context-free, do pumping lemma. The grammar is part A. The proof is part B. You are only doing one. You are not going to be you're not going to be writing out a grammar and proving it through pumping lemma as to why it's not context-free, because that's literally it's like literally like you can't have that. It can't be context-free and not context-free at the same time. So this is an example of you do either the grammar if it is context-free, or you do the proof if it's not context-free. So if you know when it's not if you know when it is context-free, guess what? You got a super easy context-free grammar question on your hand. If you know when it's not context-free, then guess what? You got a pumping lemma proof on your hand. Maybe you're someone that just wants to like throw up the proof on the page and call it a day. Well, if you can recognize when to use the proof, kudos to you. If you're someone who hates proofs with a passion, like me, then you want to know when not to use the proof so you can escape the horrible proof. So, first things first, how do we know this? Well, let's take a look at the language. B to the J, G to the 2J plus L, 4K, 3L. Where are my links? One link. That's it. Okay. It's only one link, so we don't have problems with intersecting links or links of 3. Remember, links of 3, not context-free. Not context-free if telescoping in between. L and 3L is not a link. Ooh, I didn't even see that L. Ooh, yeah. So, now we have 2 links. But guess what? They are not intersecting. An intersecting link would be like this. B, G, A, C. That's an intersecting link. This is still okay. And the reason for this is because if you're familiar with this type of telescoping problem, it actually would be okay in this case. So because of this, this is indeed context-free. I'm going to write the grammar out for this. I'm going to speed the grammar quick just to walk you through as to also why this works and why it wouldn't be okay. Can we do something without language given from written something and how to determine if it's context-free right automaton? Absolutely, we can do that right after this. I just want to give examples of what is and what isn't pumping lemma in this case. So actually, if that's the case, I'm going to do this one, another one that's given that uses the proof, and then we can do that. Okay, so a reminder, we got telescoping here and telescoping there. This is a function, and this is a function, right? So what is this composed of? Well, we know that I'm going to skip the, grammar is equal to VEPS part and just go straight into the production set. If you need more help with grammars and stuff, check out Exam 1 review videos. Yeah, definitely brush up on this. So this is composed of function A and function B. Function A is this part, function B is this part. Notice that this C is like sandwiched in between there. That's totally fine. Yeah, we're gonna get to that in just a moment. It's gonna make sense in just a moment. All right, what is A? A is this link over here. B to the J, G to the 2J. Remember, when I do a telescoping problem, the left-hand side is the left-hand side of my exponent. The right-hand side is the right-hand side of my exponent. So this is going to be my recursive case. And then this side is going to be what's inside. Well, there's nothing in between these guys, so this marks the end of this case. Function B. This is going to involve the L's now. G to the L, 1G, A to the 3L, 1, 2, 3 L's. Then I'm going to have my recursive case here, The right-hand side is anything in the middle. What's in the middle? Well, there's no plus a constant on either of these. So I'm just going to call this guy in the middle. I can call him D. D is just going to be c to the 4k. 1, 2, 3, 4. Nothing on the right. Call my recursive self and end with a lambda. This is the end of my grammar. I broke up the function into two parts because remember, this part handles the recursion of our j's. This part handles the recursion of our l's. So when you see this, you're going to see something like BGG, GAAA. Split down the middle. This is totally fine. This is totally fine. When you do a proof of this, right, you don't just say the number of G's is 2 times the number of A's, or sorry, B's, because you want to say on the left-hand side of the equation, string, not equation, sorry. Because the left-hand side of the string has its own recursive rules, the right-hand side has its own recursive rules. And there's actually a C somewhere here as well. There's like 4 C's in there. So yeah, so actually that example that you gave involves pumping lemma. And the reason for that is because of the order. Okay, well, close enough. 4k and then a to the 3l. Okay. This time, the j's are to the right. Before, it was to the left. And then the l's were to the right. So there is kind of a gap over here. This is intersecting. Because this is saying there's 2 l's to the left and then the 1 j to the right. This is intersecting. This would involve pumping lemma. This has here and here. This is not intersecting. This is just a normal grammar. Yeah, that's a great question to bring up. Intersections in between, not context-free. And if you don't believe me, wah. Ta-da! That's the answer. So notice, she filled out the grammar part, she left this part blank. If it was this grammar here with the intersections, she would have not filled out this part. She would have filled out the proof instead. All right, let's do a question that actually revolves the proof. So you see how, let's say, even if you're not good at the proof, you saw that there weren't intersecting links, and then you did the grammar. You knew you can draw the grammar. So there you go. Instant 10 points. If you can do 4 of these problems, boom, you pass with 40. Okay, question. Can I just put that not context free because there's intersections in between? So, that brings us into the proof. You are not going to get full points for that. I don't know if she gave partial credit. I will be completely honest with you. On the final exam, I ran out of time. I had like 2 minutes left, and I knew it wasn't context free, but I did not have the time, and my brain just absolutely blanked on the proof. I literally just wrote that. If you're stuck in a jam, it doesn't hurt, but you're taking a gamble with that. You can't just say, oh, I'm just going to write that and call it. I don't know what partial credit is, Overnick. Yeah. Don't gamble with partial credit. The only partial credit you can guarantee is getting credit for some parts of the question. Meaning if it's a question with 5 parts and you get 3 correct, she'll give you credit for those. If you get 1 part somewhat correct, it's a gamble. Yeah, if you're honestly not a fan of the proof, if you can recognize that, oh wow, I can write a grammar for this, I can write a regex for this, I can do whatever it is. If it doesn't violate if it doesn't violate the 2 conditions for not context free, and it doesn't violate the 1 condition for regular expression, do whatever thing it tells you to do. Regex, grammar, automata, it's literally that easy for those. When you recognize the links, if it's a regex question, or the problem links, links of 3, intersecting links, that's when you need the proof. Well, she gave you quite a bit of partial credit on exam 1. There you go, guys. There's some hope. Don't rely on partial credit. You can write anything on a paper that is not a valid argument. Yeah, please don't rely on partial credit, guys. The only partial credit that you should go for is, like, different parts of the question. Like, don't rely on getting partial credits for 1 part. Yeah, 1 point, don't get 1 point. If it's a question that has, like, 18 points, aim for, like, 12. In the sense of do 2 of the 3 parts, or however many parts it is. Like the Turing machine that we just did. If you can't do reject, do accept and diverge. Maximize the points. Anyway. Let's do a pumping lemma proof question to show what to do when you actually gotta use this proof, which I avoid at all costs. Oh, we got a good one here. Oh, this is, I think, the question that they... Wait. Oh, actually, I think this is the same question, except... Oh, yeah, this is kind of funny. This is literally pretty much the exact same question, except this time. What's different here, guys? Let's see.
There's intersecting links.
Exactly. Yeah. It's asking for if it's not regular. So we see intersecting links. Yes, it's context free, but that's not what this is asking for. It's asking if it's regular or not regular. Therefore, intersecting links are a big no-no. Just because of those intersecting links, it's no longer regular. That calls for pumping lemma. Yep. So this is context free. It's literally the same exact language that we just did, except slightly different. But the question is different. It's not asking if it's context free. It's asking if it's regular. Isn't intersecting links when the links cross over each other? Yep. The links are not... Okay. Even if the links were crossing over, it doesn't matter because the fact that there are links in the first place means that it's not regular. This question is asking if it is regular. The last question asked if it was context free. So again, same language, different question. Because this language is indeed context free, because again, there are links, but they're not intersecting. Because of that, this is not regular. This time, we're going to use our proof. So let's get our good friend, the template, in here. All right. Notice there's a regular side and a context-free side. We are using this side, the regular side. We are not using this side for this question. Because again, this is asking if it's regular. Yeah, and also, yeah, this is asking for an automaton. If this was regular, then you would draw the automaton. It's not regular. No automaton. This actually is all blank, by the way, on the actual thing. I cropped it, but this part A, is all blank. You'd leave this blank and you would just answer B. So actually, with that being said, let me paste in a blank part B and we can do it together. She will actually give you this on the exam. She will not give this to you on the final, I believe, but don't even worry about that right now. Just learn how to use the template, which is quite generous of her. Imagine you have to memorize like all of this. Yeah, don't worry, we're good. So, the blue is given to you. You do the red. So that's only half of the stuff that you really need to do. Not too bad, right? So the first part is easy. Proof that L is not regular. Observe that all words of L satisfy the following characteristic property. This part is blank. We need to do this. What do we do in this? We describe all the links. What this is saying is, okay, characteristic property in English, that's just saying, why is this not regular? You told us this is not regular, but like, why is this not regular? That's literally telling you that there's links. And the links are what causes it not to be regular. So in English, we know that there are 2 G's for every 1 B, right? That's one link. And the other link is that for every 1 G on the right, there's 1 C on the right. So we have a string that's kind of broken up into 2, right? 1 B for every 2 G's on the left, 1 G on the right for every 1 C on the right. Now, to actually write this out, we want to honestly say that, let me see. Yeah, so we can actually just say that to start off with. The number of G's on the right is 2 times number of B's. Actually, this is technically even, we could actually simplify this even more, to be honest, because we don't need to include both links. One link is enough. So honestly, we can actually simplify this much more and just straight up say, we know that there's going to be at least twice the number of G's as there are B's. I don't need to specify, oh, it's 2 G's to the left, 1 G to the right. Because again, all I care about is that there are links in the first place. If this was more specific, like if it was context free and you wanted to show there's links of 3, then you might wanna. But in this case, the number of G's is at least twice number of B's. So that is our characteristic property. Now we assume the opposite, that L is context free. Let beta be the constant, as in the pumping lemma for L. So you're always going to have a thing called a pumping constant. In this case, in the template, they always say to use pi. You can honestly use whatever they give you. Pi is usually a little easier to draw. Some of these Greek symbols are so freaking weird. And if you don't draw it exactly how it is, then you might take points off. This is my beta. It's not a capital B. It's a B with the tail on it. Fingers crossed she gives you guys an easy Greek symbol to draw out. Didn't realize this was Greek class. Haha. So we have beta be the constant, as in pumping lemma. -5 points. I cannot read that over. Yeah. Yeah. Please write legible. I don't have very good handwriting, but on this exam, I was just like, oh yeah, she does that all the time. She will straight up draw a garbage can on your exam and say that you wrote garbage. Oh, Rennick has no filter. My name was not clear enough, -2. Yeah. So, moral of the story, right, neat. All right, so let beta be the constant as the pumping lemma for L. Let W0 exist on the string of L, be a string defined as follows. W0 is your base case. This essentially says get rid of all the crap that you don't need and just show that, show the link that's causing you issues. Well, I don't care about anything else except this BJ and this G2J. All this other stuff could go screw off. Yes, there's another link in there, but one link is enough. You don't need to prove 2 links for a regular expression. If you were going to prove it's not context-free, then it's a little different, but this is context-free. Don't overcomplicate it. All you need is B to the J and G to the 2J. And what we do is we say that L gets set to 0, K gets set to 0. And what this does is it says this is to the 0, this is to the 0, this is to the 0. Those no longer exist for us. All that we're left is J and J. And we want to make sure that J is an actual number that's going to make this actually create a link. So we're going to make J bigger than our pumping constant. The pumping constant you could think of as a very small number that's going to make the window for which this string is going to pump not big enough to pump both things. When I say about window, I'm saying BGG. This is the base. Yeah, this is like induction. This literally is induction. Think of base step, inductive stuff. Blah, inductive step. This is your base step, and you're going to do an inductive step next. So this is like your base string, right? BGG. You're going to be making a pumping window that's going to be less than J. You're essentially, I'm going to honestly spoil this a little for you, but you're essentially going to be making a window that's only going to be either this big or this big. It only is going to be able to pump one symbol, not 2, because it's not the length of the whole string. So you're only going to be able to pump B's, or you're only going to be able to pump G's, not both. That's really what this proof's doing. So now W0 belongs to L because of this. I set L to be 0, the lowercase l, not the language L, and K to be 0, and I set J to be greater than our beta. So this actually, this part and this part are for this. This part and this part go for W0. Question, by pumping, do you mean incrementing a part of the string, or I don't get the concept of pumping? Yeah, incrementing a part of the string. We have a thing called a pumping window. And really what we want to prove is that having a pumping window being less than the size of the string is not going to let you pump the whole string. Think about it. If I made this my pumping window, I'd be pumping BGG, BGG, on and on and on and on. That is literally not what we want to do at all. We want to make sure that there's B's on the left, G's on the right. But we know that this pumping window is going to be smaller than the length of our string, which we're going to get to in a moment. W0 must pump because, okay, we know that it's going to be less than the length of the string. Wait, so W0 belonging to L belongs to L0 and K0. Okay, the reason it belongs to L, this string, is because this is a totally valid string. I set L to be 0, K to be 0. It got rid of this L, this K, and this L. Basically, we got rid of everything that was not our link. So just to backtrack a bit, what did we do? We described the links as first. We figured out a W0, which is a base case. And we did that by finding one link and simplifying everything else. This is the link, simplified everything else. You're focusing in on one link. That's really what this part is doing and this part is doing. We then create a pumping constant, which is given to us as beta. This is always going to be smaller than whatever our exponent j is. And doing a little bit of math, a little bit of algebra here. We're arguing that the length of this string is going to be 3 characters times whatever j is. There's always going to be 1b, 2 g's, times whatever j is. And this makes sense, right? B, G, G, G. Oh, oops, sorry. B, G, G, if j is 1. BB, GG, G, G. 2 B's, 4 G's, if j is 2. 3 B's and 6 G's when j is 3, etc. With that being said, W0 must pump because its length is always going to be 3 times j. And because we proved that j is always bigger than beta, if we were to say 3 times this whole thing, right? Actually, let me do this down here. This is the same as saying 3 times j is greater than 3 times beta. Right? That makes sense, right? J is always going to be greater than beta. Beta's our pumping constant. We always want the window to be smaller than the length of the whole thing. And we know that 3 times beta is going to be way bigger than beta on its own. So this is the end of this step over here. We are done with half the proof. Just going to pause for questions here. We defined the links. We made our base by simplifying everything else. Our pumping constant's less than the exponent. And the length is 3 times j, because remember, the base is going to be 3 characters. If this was something like, I don't know, b to the 4j, c to the 3j, it's 4 plus 3 is equal to a base length of 7 times whatever our j is. So I hope that clears that part up. And now we know that 3 times j is greater than 3 times our beta, because remember, j is greater than beta. J is greater than our pumping constant. And 3 times the pumping constant is greater than just the pumping constant by itself. The 3 is, so the 3 comes from the length. So again, if that was like, I don't know, b to the 4j and g to the 2j, it's 3 plus 2. The pumping constant is the length of W0. Close. It's less than the length of W0. We know 3 times j is the length of the string, right? Length. This is greater than 3 times the pumping constant because we've established the pumping constant is always smaller. So the pumping constant is always going to be much less than the length of the whole string, because what are we trying to prove? We're trying to prove it cannot pump in a window that small. This is why we're proving that this window, this pumping constant, is too small. That's really what we're trying to prove here. The pumping constant makes too small of a window, and because of that, you can't make a pumping of the string, you can't make the string bigger by pumping, keeping the same ratio of the B's and the G's. So if the length of the string is greater than PC, then we can pump. So the length of the string is greater than the pumping constant. And because of that, we can pump regardless. But when we pump the next part, we're going to show that what we pump is too small. Think of it this way. Let's say you get a shirt, right? And this shirt gets shrunk in the wash. And you decide that you're going to use this as a template for more shirts that you're going to create. Well, if your shirt is too small on you, it's only going to cover part of you. You can make 100 of these shirts, but the one shirt is going to be way too short, and it will not cover all of you. If you want the shirt to cover all of you, then it needs to be equal to or greater than the size of the string, your body. Likewise, our pumping constant is too small, it's too short. It's not going to encompass the entirety of the string. So even if you pump 100 times, your ratio is going to be way off. Yay, glad to hear it makes sense. No problem. All right, next part. By the way, we're down here now, for if anyone's lost. I know it's a lengthy proof, but once you get it, it's honestly, it's not that bad. And this is coming from a big proof hater. Like, I really don't like proofs, but it's not horrible. So in any pumping decomposition of W0, the pumping window satisfies the following property. So what is the issue? Well, the shirt is too small. It's only going to reside in one segment, meaning I'm either going to pump B's or I'm going to pump G's. It's either I put this piece of fabric on like the top half or the bottom half. Actually, it might have been better if I used a dress as an analogy. It's a piece of fabric and it's only going to either, or a towel. Okay. Think of a small towel. The towel's either going to dry the top half of you or the bottom half of you. It can't dry both sections at once. One side is going to be dry and the other side is going to be wet. Think of a towel. There you go. So this towel is only going to be in the B's or the G's. So this pumping window satisfies the following property. It resides in only one segment of B's, right? It's too small. It can't stretch. It can't stretch to those G's. Because remember, this window is too small. And why is this? Because it's always going to be equal to B to some P, where P is greater than 0. So we're no longer using J for this exponent because now I can't say J anymore because that would mean there's a link between them. But there's clearly not a link anymore. If this is only in B's, and let's say I print out 2 B's, I pump it once, I never pump the G's. The link's gone. There's B to the P now, where P is equal to 2, and G to the J, where J is equal to 1. We have a major issue. And this is exactly what we're going to do here. By pumping one time, we obtain a string that looks essentially like this. B to the J plus P, right? Whatever J is, which J is equal to 1, which gave us the 1B, but we pumped it once, so that's how we got this P here. And then G to just the J. Oh, 2J. Sorry, because that was what it was originally, right? 2J. So 2 G's for every 1B. But this time, I pumped it once, and I only was able to pump the B's. I stretched out that towel only over the B's. Because of that, the B's got an extra B. That's where this P comes from. And G's got nothing. The B's got dried by the towel. The G's did not get dry. They're soaking wet, and they're very upset. How dare you break our link? This violates the stated property because now the number of G's is equal to greater than 2. Wait, the number of G's is equal to... Okay, the number of G's is now less than twice the number of B's. And this is what we say in the characteristic property up here. Remember, the number of G's is at least twice the number of B's. Well, now the G's are less than 2B. So this is no good. And thus, the string does not belong into L. Since L violates pumping lemma, L is not context-free. That is the end of the proof. I'm gonna post her answer as well here, so you can actually see what she wrote. She wrote it just more detailed than I did. Okay, well, that's the end of the pumping lemma question. Questions, comments, concerns?
I have a question.
Sure.
Um, like we proved the first link and second link, right? So sometime like we have palindrome in the middle, so we can by setting by zero palindrome part we can take it out and then still we can prove both sides.
Yeah, so a palindrome is a very popular question for this. And
Mm-hmm.
if you're ever asked a palindrome, you want to get rid
Mm-hmm.
of everything else. So you see how we made all of the other
Yeah,
exponents
yeah.
to be zero?
So my
Mhm.
question is, I can get rid of palindrome too, right? And just prove to link the beginning or last part.
Depends on what this question is asking. If there are links and it's proving to be not
Like
not
like like two of n like a to n and middle palindrome bb and then b to n. So I can take out bb by setting it as 0.
yeah, if it's yeah, whatever the exponent is, you set the exponent to 0 and you just get the palindrome itself. And the palindrome is
Oh,
essentially going to say that there's going to be kind of a link between like the first character in the palindrome and the last character in the palindrome part. So if it's BAB, you need a B in the beginning and a B at the
mm-hmm.
end. That's the link that you're going to be proving. So similar to this, but just that palindrome part where the first and the last symbol are going to have to be equal as well as everything in between.
So we have to prove only palindrome part, not
So,
or we have to prove also palindrome too. Like
okay, going back to this, right? If the question is asking if it's regular or not, all you care about are links. Any links that exist, boom, it's not regular. If it's asking if it's context free or not, then you have to pay attention to the links. If there's 3 or more links of the same letter, then you have an issue. But also if there's intersecting links. So thinking of a palindrome, right? Let me
yeah,
change the color of this. Let's say I have a palindrome ABCBA. And let's just say there's like AABB. Just these guys in the middle are a palindrome. I don't care about these two. If this was like B to the J and G to the J, I would set J is equal to 0 and get rid of both of these, just focusing in on the palindrome. The palindrome part has a link here and a link here. So if you notice, these are actually not intersecting. This is on the inside,
regular.
this is on the outside. It's telescoping.
Yeah.
So that would be what you're proving in that case. So this would not be regular, but this is totally fine to be context free. Yeah, there's
Okay.
links, but there's not a link of 3. It's not like you're saying that it's linked over here as well, like 1, 2, 3. And it's not like there's a link over here that's intersecting. All recordings will be in the Everything That You Need to Succeed channel. Quite literally, everything you need to succeed will be in that channel. No problem. Yeah, so that's like how you would do like a palindrome kind of problem.
Okay, thank you.
No problem. Question, we violated the standard property of G is less than or equal to 2J because... let me just go back to that one. So G is less than 2B. This is saying that the number of G's is no longer less than, no longer at least twice the number of the B's. Because what was our characteristic property? The number of G's are at least twice the number of B's. We know this because there's going to be 2 G's for every 1 B. At the minimum, because of also this part here, which technically gives us extra G's that are not part of this link, because we're only dealing with one link. So this violates that because now when I pumped the string, there's no longer more B's than 2 times the number. There's no more than 2. Sorry, I just had a brain fart there. There's no longer twice the number of G's compared to B's. The ratio is messed up. That's where we got it from. The whole thing is we pumped too small, we shrunk the towel in the wash, it can't extend over the B's and the G's. So now when you pump the string, you make another string, you're only drying one part. You're only pumping one part. And that does not make it with the same ratio. Yeah, so it's 2 times the number of B's for G's. That's the characteristic property. Yeah. It's the amount of times that we pump. So anytime that we pump, we can't use J anymore for the pumping because that means we have to pump both the B's and the G's, and our pumping constant, our pumping window is too small. So when we pump, we're only pumping the B's. So the P is telling us how many times we're pumping the B's. It's a bit of a mouthful. Think of it how many times we're drying one part with the towel. We're never going to be able to dry the other part. The towel will not be big enough.
Thank you.
The first video is not posted because it's really long. It's probably gonna take till later tonight. Yeah, it's honestly still processing on my computer. Yeah, it's gonna take a while. That's why I wanted to separate them. So if P is equal to 1, we pump in another B. Yep, if P is equal to 2, we pump in 2 B's inside beta. Yeah, etc, etc. So here we wrote out the context-free grammar and show the proof to... No. This is asking if it's not regular. All you care about is writing the proof. You either make the language or you do the proof. This is saying it's not regular. Therefore, you can't write a... Okay, they're asking for an automaton. But we know it's not regular, so we do the proof. It's either or. You do not do both. You're always going to have one part blank. Don't even like exit out or anything. Just leave it blank completely. You can actually see on like the solution keys, like it looks kind of like she didn't answer part, but that's on purpose. only do one or the other. Question, wouldn't this be true for all strings where we introduce a constant p? Yes, but we're only introducing the constant p for the b's. This is only saying, because we've established that the pumping window is small. And because it's so small, which we've established, it's less than the length of the string, right? It's less than the length of the string, which is less than the length of 3 times that. Because of this, you can only pump the one segment, which we said here, right? The pumping window resides only in the one segment of B's. So we satisfy that when it gets pumped, it's going to be B to the P to represent the number of B's getting pumped, because only B's are being pumped because the pumping window is too small for everything. Better? Let that sink in a bit. The J and the okay, the 2J and J. Okay. So J is, yeah, so you can kind of honestly prove it on either side of the link. You could also have proved it with the G's as well if you wanted to do it backwards. But you know your window is not going to be equal to your pumping, your pumping window is always going to be less than the length of the string. So you're only going to be able to pump one segment. The towel's only going to fit around your top half or your bottom half, not both. It's too small of a towel. It's too small of a pumping window. This is also very relevant with grammars, because imagine you have a 3 link, right? A link of 3. You're only able to pump up to 2 segments. You can't pump 3. The towel will not be big enough. The pumping window is not big enough for the whole string. That's really the whole gist of this proof. Yeah, but this case, the B's are the smaller of the pair, so we kind of just used them in this example. Is there ever a case where the pumped equation is valid? Yes, there is. Guess what? That's if it was regular. Which actually, let me show you. I don't know where my pencil went. Oh, there we go. All right, if this was B to the J and G to the K, 2K. BGG, right? Guess what? There's no link between them. I can set J equal to 3, K equal to, let's say 4. And this is going to make BBB, and then 4, 5, 6, 7, 8. Notice that there's no link at all. There's no rule in between. I can pump one side, I can pump the other side. It doesn't matter at all. There's no dependency between the two of them. J is its own unit, K is its own unit. They can do whatever they want. You can pump the J's, you can pump the K's. We know that the pumping window is still going to be, less than the whole length of the string, but that doesn't matter, because guess what? even if you only pump one, there's no property that's getting broke. Yeah, you never face that because then you just do the grammar, or in this case, you would do a regex. Is the pumping window the only place on the alphabet in the regular expression, and can it place between the letters in the context-free grammar? I don't really understand your question. Let's just do a context-free grammar example. I think that might clear things up a bit. It is getting a little late, so I think this might be the last example of the night. I'll still accept some questions and everything, but can you do one where it's regular? We did one already that was regular. You just do the regular expression or the automaton. So if that was like literally something like this, b to the k, g to the 2k. No, we want different. We don't want links. B to the j, 2j, right? Okay, yeah, if this is asking for an automaton like this is totally fine. There's no links. This is regular. 1b for every 1b, and then bring that back, and then g to the 2j, g, and we want to make sure that we don't accidentally loop back, so we're going to have a lambda transition. Right, because if I accidentally looped back here, I can loop back here again, and we don't want that. So G and G. And I could finish there. So this would be an automaton, because this is regular. This is totally fine. There is no rule. I can just do a loop of B's as many times as I want, and then after, move to a loop of 2 G's anytime I want. The only rule is it's always 2 G's. So actually, the end would be here, not here. The reason being 1G, 2G, end. You have to end every 2 G's. This is an example where it's regular. Yeah, I'm pretty sure there's a Rice and Clean's theorem video somewhere in there. If someone could honestly find that and post that somewhere in the server, like repost that somewhere, that would be really helpful. Yeah, I don't really have the time to go over that part tonight. I'm just gonna go over one more example, this time proving that it's not context free, and then that'll kind of be it for tonight. I just want to make sure, like, you know, you guys have like some examples to go over, because as long as you understand the proof, you can like apply this to anything. Get your links, make your W0, prove that it's your pumping constant smaller than the window, pump it once, boom, invalid string. Alright, I'm gonna just clear this out, and I'm gonna get a grammar in here. Okay, that one is a grammar, and this one looks like it's fun. Also, I'm kind of hungry, so I'm probably gonna eat dinner after this. So, all right. Notice that this one is not a exponent one, right? We have to kind of make the language ourselves and go from there. So this one's going to be a little bit more tricky, but it's good to know these two. So we're over the language of our sigma, A, B, C, G, that consists of exactly those strings over sigma whose length is even and greater than or equal to 4, but the two symbols in the middle are different from one another. Okay. Now, at first glance, you're probably saying, oh, isn't this just one of those, I don't know, those regular expressions that can just be like whatever in the beginning, whatever in the end. You need at least, and then you just need case here where it's A, B, B, A, C, A. No, that's not the case because of this thing here, greater than or equal to 4. If it was less than or equal to 4, good news, the string is not infinite, and you can do a regular expression. As soon as it's infinite, it is not context-free. I mean, not regular. As soon as it's infinite, it is not regular. Because think about it. You can't make a regular expression to encompass every single thing. You could have a string length of 1,000,000. You can't write that out. That is something that is infinite. I mean, maybe countably infinite, but you know the structure of it, but it's infinite regardless. You can't find all the options in that. We know because of that, this is not regular. So with this being said, we know that there are links in the middle here. Whatever is in the middle has a link. So these middle symbols have a link between them. It could be whatever in the beginning, whatever in the end, but those two middle symbols have to have a link. And on that note, in order to make sure they're in the middle, this has to be equal to this. There's an equal number of characters here and here. So because of that, let's actually see what she said as the characteristic property. Actually, let me just post a picture of the proof in here. So again, we know that it's not regular, so we are not doing the state transition graph, we are doing a proof. If it was regular, you do the state transition graph, but guess what? Anything infinite, you can't do a regular expression where, well, okay, you can't do it because it's infinite, and also because you have to determine what the middle is. If it was infinite and you didn't need to know what the middle was, then you'd be okay. But how are you going to decide what the middle is if it's infinite? With that being said, the length is equal to 2n for some n is greater than 2, and the nth symbol is... Okay. All right. So what are our two problems? We know that the length is even, greater than or equal to 4, and the two symbols in the middle are different from one another. The issue here is that our length is equal to 2n, where n is greater or equal to 2. Right? That satisfies this part here, greater than or equal to 4. 2 times 2 is 4, minimum length of 4. And we know that the nth symbol from the left, what is that saying? There's n characters here, this middle symbol is not equal to the nth plus 1 symbol from the left. And that's literally saying n symbols this way, what is the symbol next to it? 2 middle characters. This is our characteristic property. This handles the infinite part, because we know it's going to be even and greater than 4, which we prove here. And we know that these middle symbols are not equal. That's the characteristic property. Now, next, assume the opposite, that L is context-free. Once again, we're letting beta be the constant, as in the pumping lemma for L. Let W0 exist on L and be a string as defined as follows. All right, we're going to make a base string. This string is going to literally just be the parts that we need to pay attention to. So in this case, we want to take into account our W0. Wait, I thought this was nth2 symbol and nth2 plus 1. N is defined as to be greater than or equal to 2. That's why we know it's the nth symbol from the left. So if n is equal to 2, right? 2 times 2 means the length is 4. Nth symbol is 2. Middle symbol and nth plus 1 symbol here. 2 middle symbols. I think you could also probably do it that way too, but we already defined it in this case that n is greater than or equal to 2. Yeah, no problem. So our W0 is just going to involve both sides of this string. We're going to define an a to the n and b to the n. N is going to always be half of our string, right? If n was 3, it's 3 times 2. 1, 2, 3, 1, 2, 3. This is our a, this is our b in this case. Right? We divide it into 2, make it easier for ourselves to make sure that it's always equal. Notice that there's now a link between these guys. We made a link. Wow, I wonder what that reminds me of. Context-free grammar. Yeah, I know, no way, right? There's a link between the characters. We have to have an equal number of A's and B's. Sounds a little familiar. We just need to define one last thing. We know that n is going to be greater than 2 plus, wait, why plus the beta? I think, okay, I'm honestly a little bit confused on this part, but I think the reason that we're doing this is because we know that these two characters are the ones that matter. I think we're going to kind of prove that if we shifted that n to be greater than 2 plus the pumping constant, we're essentially saying that it's now not just 2, it's going to be kind of shifted over a bit. So now this becomes our 2 characters, and this is no longer in the middle. I think that's what they're trying to say here. This one's a bit of a trickier question. It's not as straightforward as the other one. Okay, it says W0 belongs to L because, okay, we know that the length is even, right? 2n. And it's equal, the length is equal to 2n. And we know that this is greater than what we just defined here, right? If I were to multiply this whole equation, I'd get 2 times n, which is greater than 2 times 2 plus our beta constant, just like what we did before, which is greater than just our beta constant. our pumping constant, which is beta. Okay, so bit of a little confusion there, but we're essentially saying the length is even, and if we were to multiply 2 by this equation that we made here, we get this. And this is saying that our pumping constant is always going to be small. It's going to be too small to pump the entire segment. It's only going to pump this side or this side. It will not pump 2 times n, which is our length. This is what we're proving here. Okay? Pumping constant is too small to pump the entire length of the string. It will only pump this half or this half. Will not pump both. W0 must pump. So this W0 we created must pump because its length is equal to this. Yeah, okay. So we know that it must pump because it satisfies this property. So this is totally fine. As someone said before, wait, is it able to pump? Are we seriously able to pump here? Yeah, we can pump, but it's not going to pump that right thing. In any pumping decomposition of W0, the pumping window satisfies the Pauling property. Simply, it's going to be way too small. It's going to reside in either the segment of A's over here. Let me just rewrite this because it's getting kind of confusing. It's going to be either here or here. It will not be in both. So it's going to be either in the A's or the B's. So in this case, let's just say the A's, just to make it simple, because this is the first segment. It resides in the A's, and now we're going to make our own pumping, we're going to make a variable to show how many times this pumps. So it's going to reside in the A's for some A to P, where P is greater than 0. Very similar to the last one. And this is because it's our pumping constant is way too small to reach over to this side. By pumping one time, we obtain a string that is going to violate this property, right? We're going to get a string that's kind of like this. A, 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 A. Oh no, there's an extra A. B, B, B. The B's never got pumped the same number of times as the A's. So now we have A to the, what was it? N plus an extra J. Oh, sorry, plus an extra P, right? Because P came from the times we pumped it. And B just gets pumped N times. So because of this extra P, it violates the characteristic property. Because now, first of all, the A's are not equal to the B's, right? The segment of the A's is not equal to the B's. And because of this, we can't control what part is in the middle. The nth symbol and the nth plus 1 symbol are in the A component. We know this because there's 1, 2, 3, 4, 5, 6, 7. Actually, we probably should make there 8 because you keep it in even terms. And if I were to find the middle now, I pumped it once, there's 2 extra A's. 1, 2, 3, 4. 1, 2, 3, 4. This is the middle. This is the nth symbol, 4, right? This is the nth plus 1 symbol. Oh no, they're both A's. These are no longer directly, even though they're in the middle, we're only controlling the last A and the B. These are not the right symbols. This string does not belong to L, violates pumping lemma. L is not context free. That was much harder than the other one, but if you get a problem like this, you want to try to make it into links that you can deal with. So this is irregular and context free. Yeah, it's not regular. Oh, no. This is not context free. Wait, hold on. I'm sorry, this is not regular. I'm sorry, this is actually... It's the same proof, but I ripped it off the wrong question. Yeah, this is irregular. So this is not regular. Yeah, context free, we have a link. Oh, I just realized I did not do the context free problem. Okay. Yeah, so actually, this was not the question I wanted to do. I just realized that. I'm going to speed run quickly through a context-free problem, and then I'm going to call it quits for tonight, because I think it's going way too long of a review, honestly. So let me do this one super quick, and then I'm going to end it here. I'm actually just going to use her answer for this one. Just because it is getting a bit on the late side. This one's a little bit of an easier one. Okay. All right. This one is proof that L is not context-free. This one is actually not context-free. Okay? Why is this not context-free? Let's take a look at our links. J, for K, for L, oh, for J. B to the J, G to the 2J, A to the 4K. Links of 3, not context-free. Boom. Automatically know this is pumping lemma. Links of 3, not context-free. So if you're someone who might not be good with pumping lemma, and let's say you only want to do the ones that are context-free or the ones that are regular, skip this one. If you like pumping lemma and don't like the other questions, do this one. This is a way to kind of find out, okay, do I use pumping lemma? Do I use regular? Do I make a regular expression? Do I make a grammar? Do I do this? Whatever. We know how to solve this now. So we're going to just do this the same way that we did the other one. Observe that all elements of L satisfy the following characteristic properties. Same thing for context-free. We have to show what the property is. What is our property? There's a link between the J's. There's one B for 2 G's and 4 A's. But we need to be a little bit more specific than that. So we're saying the number of A's is is twice the number of G's and is 4 times the number of B's. So that's what we say over here, right? Just identify what the property is. Now we assume the opposite, that L is context-free. Once again, I guess on this exam she wanted to use beta all the time. We're going to assume that beta is our pumping constant. We're going to once again make our W 0. Once again, we're going to get rid of everything else. So once again, get rid of everything else. K is equal to 0. L is equal to 0. We make a string that is literally just B to the J, G to the 2J, A to the 4J. We got rid of C to the 4K, C to the 3L, because we made K and L equal to 0. Just like last time. We know that J is always going to be greater than our pumping constant. Our pumping constant is always smaller. Pumping constant is small. Now we say the W0 must pump because of its length. The length is always going to equal, how many characters are there? Well, in my base case here, 4 plus 2 plus 1 equals 7. 7 characters times whatever J is. So if J is 2, then there's 14 characters. You get the picture, just like the problem we did before. 7J. Now, what we do to one side of the equation, we do to the other. Greater than 7 times pumping constant, and 7 times our pumping constant is greater than just our pumping constant itself. That's just what she has right here. Okay? In any pumping decomposition of 0, pumping window satisfies the following property. What's our problem? Well, this pumping constant is too small. It will not cover the entirety of our string. It can only cover one segment or 2 segments at most. It can't cover all 3. Now remember on the last proof we said that it will not be regular because a regular can only handle 1 segment. Context-free can telescope 2 segments. We know this because the last problem had something like this, right? 1 on this side, 2 on this side. I could just make a grammar that says, do that, right? Just have something here and it pumps this side, pumps this side. That's totally fine in context-free, but how are you going to do that when there's 3? You're either going to pump 1 segment or 2 segments. Only 1, maximum 2 segments can be pumped. So we see here, in any pumping decomposition, W0 satisfies the following property. It resides within a single segment or within 2 adjacent segments. What that's saying is that I can pump only A's, I can pump only G's, I can pump only A's. Wait, I can pump only B's, G's, or A's. Or I can pump adjacent segments. I could pump the B's and the G's, or I could pump the G's and the A's. Cannot pump anything else. I cannot pump the entire string. This is because we know that it's going to be shorter than our pumping window. We just proved it over here. Our pumping window is too short, cannot have a part in 3 segments, because then it needs to be greater than the length of our J. This can't be true for it to be actually pumping the entire string. The pumping window is too small. So we prove this by pumping a string, pumping 1 time. You get a string with 1 segment, but no more than 2 segments longer than the corresponding segments in W0. Okay, what that's saying is we get a string that pumps 1 segment or 2 segments. It cannot pump all 3 segments. Your answer does not need to be exactly like hers, by the way. Like, you don't have to be saying word for word Obernic language. You can say it other ways too. Yeah, so the pumping constant is always less than j. So we obtain a string with at least one segment pumped, but no more than two segments pumped. These segments that are pumped are the only ones that are longer than their corresponding segments in W0. They're longer segments, which violates the stated characteristic property, blah, 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 because it has one segment. What did I say here? Got cut off. One segment that is longer than the correct relative of at least one other segment. Okay, what is our characteristic property? The number of A's is equal to twice the number of G's, and in turn equal to 4 times the number of B's. In English, you can say something like one segment is no longer in the correct ratio to the other segments. Simple. Or if you want to write it out, like either the number of A's is no longer twice the number of G's and 4 times the number of B's. You get the picture. You're not able to pump the whole string, you're only able to pump part. The ratio is gone. This string does not belong to L. Violates pumping lemma. This one is not context-free. That was a bit rapid fire through that one, but I wanted to make sure you got at least one context-free one in here. But you see how it's a lot of repetition. The more you do these problems, like, the better you're going to get at it. Like, you're going to recognize patterns, and then it's just literally going to be regurgitating a proof on the exam. Write this out like 10 times, and it's going to be ingrained in your brain. You're going to have dreams about pumping lemma. Let's hope not. All right. That's the end of that one. Before I end the session, any questions? Went a bit longer than I had hoped, but it's okay. You guys can go over this too, so don't worry. Okay, I saw two problems in the past paper. Language is equal to G to the K, B to the L, C to the... Can you explain the difference? Oh, okay, I see what you mean. Okay. This is a matter of overlapping links. So, okay, I'm just going to use actually, G to the K, B to the L, C to the J, A to the M. Okay, wait, are we saying something like this? I'm just a bit confused. Say K plus L, and this is L. Like something like this? Because this, yeah, okay, gotcha. Okay, awesome. So, all right. This is g to the k. This is b to the k. This is b to the l. This is c to the 2l. We break this up into two parts. G, b, b, and then c. And then we don't really care about this a, honestly. The left hand of this side is its own thing, and the right hand of this side is its own thing. Would that be the grammar one, meaning it's regular? This is regular. If I were to switch it up and do it this way, I don't believe this would be. Because now the L's are on the left, and now the L's are in between the K's. This is intersecting. This is not regular. Watch out for intersecting links. That's really what you want to watch out for. Yeah, absolutely. They do matter. The order of the variable exponents do matter, as you can see here. This is a very good example of that. So watch out for that on the exam. It's not context-free if there's telescoping in between. All right. So any other questions? Both of these actually are context for, wait. No, I'm sorry. Wait. There are links here. This is not regular. I'm so sorry. Okay, the left one is context-free. The right one is not context-free. I'm not thinking correctly. Yeah, links equal not regular. Both of these are not regular. This one is context-free, though. This one's not context-free. Yeah, that's... Thanks. Yeah, I need a break. All right, I'm gonna end it here. Best of luck studying, guys, and just try to focus on what you feel most comfortable with. You saw the breakdown of questions, so do with that what you will. And yeah, best of luck, guys.